Thanks for sticking around for the distinguishable talk of the session. This is joint work with Azad Farzan and Derek Dreyer. And the basic observation of this paper is that proofs of relational properties are not compositional enough or don't compose well enough. And we propose that the idea that you can solve this problem if you think about relational proofs in a slightly different way. So the goal of the paper is to bring compositionality into relational proofs of hypersafety properties. So we're going to first look at what hypersafety properties are, then what we mean by relational proofs, and finally, what's the problem of compositionality and how we solve it. So first, let's have a look at hypersafety properties. So here's an example of a normal safety property. We're all used to it. Here, I'm representing it with a normal Hort triple. I'm stating with the Hort triple that F is computing multiplication of A and B in the variable R. K-safety, on the other hand, is a relational property about multiple runs of programs instead of a single program. And in this case, I want to specify that F distributes over plus in the second argument as a relational property over 3 runs of F. And I would write it this way if F was a mathematical object, but instead it's a program which has state and effects. And so I'm going to represent that property using a hypertriple, which is a triple where in the middle we put more than one program. Here we are putting the 3 instances of the call to F that we were looking at in the previous equation. So a little bit more formally, hypertriples are triples with pre-condition, post-condition, and in the middle we, instead of having just one program, we have k terms taken from, in this case, just for simplicity, a simple imperative language, sequential language. The meaning of a hypertriple is saying the following. So if you look at every possible input and output store of the semantics of each term, if the input stores relationally satisfy the precondition P, then the output stores relationally will satisfy the postcondition Q. One example is determinism. Here we have in the middle 2 copies of the same program, and we're saying if we give to them the same inputs, we're going to get the same outputs in return. Hypersafety properties arise from a variety of domains. Examples come from security, like non-interference. We can have examples from verification of correctness of optimizations, like translation validation. And in general, we have also algebraic properties like distributivity that I mentioned, or monotonicity, idempotence. So how do we go about proving these properties? So one possible naive approach is to say, okay, let's have a look at hypertriple and see how we can prove it. We have here an instance of the distributivity property that I showed you before, but for a specific program. And we can say, okay, we can look at every single program in the triple and try to figure out what it does. Here we can have a look at the code, and what it's doing is iterating A times, and every time it iterates, it's adding B plus C to the accumulator. Okay, so we figure out quickly that what the accumulator will store at the end is the multiplication between A and B plus C. Fine. We can repeat the process and look at the other 2 instances, and we figure out that they are also computing some multiplication. And from the properties of multiplication, we can manipulate the 3 postconditions to realize that, in fact, the first accumulator contains the sum of the other 2. Now, this is a valid approach because it proves the property, and it corresponds basically to a reduction from hypersafety to safety, because we looked at every program in isolation. But this reduction has a very high cost. We were looking at a very weak property, which is distributivity, which doesn't talk about the specific functionality of the code. And instead, we are forcing ourselves to really understand what's the functionality of this piece of code. In this case, we really needed to characterize multiplication. And we can do better than this. So the insight behind relational proofs is that it's advantageous to look at the three programs here at the same time and do a proof that considers all of the three instances at the same time. For example, here we can establish a relational invariant between the states of a lockstep execution of the three instances of the program. For example, at the beginning, we can establish that, yes, the relation between the accumulators holds at the beginning because they're all 0. And if we execute one instruction per thread, per program, at every step of the proof, we can reestablish this invariant. In particular, the while loops are looping the same number of times in all three instances, and so we will have one instruction matching the other programs in the proof. And after the first iteration here, we see that, well, in the first program, we are adding b plus c to the accumulator. In the second, we are adding b, and in the third, we are adding c. And so the relational invariant is preserved. We can use that relational invariant as a loop invariant, and we prove the property, because the relational invariant implies the postcondition, without having had to really characterize what the program did at any point in time. In fact, if the accumulator was updated in a different way, that does not amount to multiplication, but to some distributive function, the relational invariant may still hold, and we may still be able to do the same proof without changing the invariant. And so we are really proving a weaker property, and we get a simpler proof as a result. At the core of the core principle behind this lockstep alignment of programs strategy for the proof is what we call lockstep sequence rule, which is depicted here. The idea is that the rule matches on two programs that have exactly the same structure. They're both sequential compositions. And we want to think about the first two steps of the two programs relationally together in the first premise, and the second two steps of the two programs relationally in the other premise, and put these two together in a relational property of the composite programs. This approach was pioneered for tool safety by relational Hoare logic and extended to case safety in Cartesian Hoare logic. And this led to logics that, of course, were more sophisticated than what I'm presenting, because programs in the wild are not always perfectly aligned when you load them in a Hypertriple, and so you need to push the expressiveness of how you can align them in the logic. But this can be pushed forward, and it leads to nice automation techniques. Because the proofs are much simpler, there's much higher probability of getting a proof automatically. Now, these are good proofs and good results that we want to leverage, right? The problem is that we cannot build this way all the proofs that we want. So we need something extra. What are the proofs that we want? So ideally, we would be able to build compositional proofs of relational properties. In this example, I suppose I'm writing a MapReduce function that takes a user-provided function f as a parameter, and we want to prove that our implementation of MapReduce is deterministic. And the determinism of MapReduce may not rely on the specific functionality implemented by f, but only on some relational abstract properties like determinism, commutativity, and associativity of f. All of the properties that I mentioned are hypersafety properties expressible as hypertriples, and so we should be able to take these hypertriples for f and mix them together in a proof for the MapReduce. There is an immediate problem that you face if you try to implement this strategy. And it can be observed just by looking at the arity of the hypertriples. In general, you will need to mix triples of mixed arity, while the basic principle of lockstep derivations will keep the arity constant, right? Here in the Lockstep sequential rule, all the triples have the same arity. And in general, the previous work kept the arity constant throughout a derivation, except for the escape hatch of failing back to the single component reasoning that kind of forces you into this characterization of functionality trap. Even in the case where all your triples in the goal are of the same arity, there's still a problem. So the problem runs deeper. And I want to show you exactly what's going on with a simple example. So here I want to be able to assume some axioms for the function op that I'm treating as a parameter. And here I'm assuming a determinism triple for hop and a commutativity triple for hop. And I want to prove the hypertriple at the bottom. What the hypertriple is saying is that if I compute op of AB in X on one side, and on the other side I do the same, but I also repeat the process with B and A exchanged, and I save the result in Y, all these variables will have the same value. This should be trivially satisfied because of the axioms we know about op, it's deterministic and commutative. Now, if we apply the alignment strategy to this problem, we are able to get through the first two assignments. They're perfectly aligned, and if you look at them, they perfectly match the information that is in the determinism triple. It says that if you start from true, you get the same result in X on both sides. Fine. The problem is, when you try to look at the second assignment on component 2, it is not matched by anything on the other side. We are left with one call of op, and we have no axioms that talks about one single run of op, right? We need some body for it so that we can apply the axioms. So what was possible in the literature before was that for specific instances of op, where we have the code and we can maybe reanalyze it, right? You could maybe come up with some proof. But these proofs were never going to be generic on the hyperproperties that I showed you, and even they could not reuse the hypertriples I showed you if they were available. So this is clearly not good enough. And ideally, we would be able to construct a proof that uses the assignment of X on component 1 twice. One for the alignment with the first assignment on 2, and once for the assignment to Y, because then that alignment corresponds exactly to invoking commutativity. But when is this sound? How is this sound? How does this generalize, right? So what we say in the paper, basically, is that the essence of relational proof is not program alignment, but is keeping the effects of computation implicit. This fact that you're not forced to characterize what a program does, but you can keep it there in the judgment with your assertions and just say whatever it does, this holds. This leads to our contribution, which is the logic of hypertriple composition. It's LHC. It's a logic that takes this principle of keeping computation implicit and expresses it as focusing on hypertriples of mixed arity as the fundamental building block. So the first thing that LHC introduces is a weak-spree assertion on hyperterms. So let's see how this works first, and then I'll show you how it solves the problem. So technically, we have hyperterms, which are not just a single term, but a finite map from indexes to terms. These are the tuples of programs that I showed you before. And they have an effect on hyperstores, which are maps from indexes to stores. So what's the semantics of a hyperterm? Well, it will be defined on a finite number of indexes, here 1, 2, and 3 in the example. And if we feed to it an input hyperstore S, we will obtain the output store S prime, where at each component we apply the corresponding term, semantics, right? And for the indexes where the hyperterm is not defined, we just propagate the state untouched. With this semantics, we can define the weakest precondition, which is an assertion over input stores. You give me an input store, and it either holds on it or not. And it holds on it if for every output store that you can reach from it, the postcondition will hold on it. So it's only true on the hyperstores from which you will reach something in the postcondition. We define the turnstile as implication between assertions, and normal hypertriples can be encoded as weakest pre by saying the precondition implies the weakest pre. How does this solve anything? So the idea of the weakest pre is that it's an assertion. You can place it wherever you want to place you can place an assertion, but it has the term there, and it's saying whatever the term does, Q will hold at the end. And this is what we're going to leverage. Because now this is an assertion, we need the logic to be able to talk about this assertion as a primitive concept, right? And this is what LHC introduces as a second crucial contribution, and it's a number of new reasoning principles for composition of weakest pre that are on hyperterms. And we classified these new principles in 3 classes. The first one is about unioning two hyperterms, T1 and T2. The second class is reindexing, manipulating the indexes of the hyperterms. And the third class is removing components from hyperterms. So we'll focus, just to give you a flavor of how this works, on the class of rules that talk about union. So here I have my running example that we were stuck with before in weakest pre form. Nothing really fundamentally changed here because all our preconditions before were true, so we're fine. And to prove it, using LHC, I will need some standard rules. Here, these are standard rules, but in weakest pre form. So we have the rule of consequence that allows you to weaken a postcondition, the rule of frame that tells you that if you need to prove P holds in the postcondition, but P does not refer to variables that are modified by T, then you can just prove it in the precondition. And the sequence rule that tells you that if you need to prove the Q holds after you've run T1 sequence T2, then it's equivalent to say you need to prove the postcondition Q after you run T1 and after you run T2. In addition to these standard principles, we need 2 novel rules of LHC. The first is nesting, that talks about this joint union between hyperterms. So this works just by putting together 2 hyperterms that work on these joint sets of indexes. And it says that the triple on the union is equivalent to a nested version of the triple where you have T1 first and T2 second. We'll see how this helps with anything in a second. The second principle is the conjunction rule, which is, you can think of it as an extension of the normal conjunction rule for Hoare logic, and it works on overlapping union. So you can have the 2 hyperterms T1 and T2 overlap on some indexes, provided that they map to the same terms, and in that case, the overlapping union just unions the maps. And in this case, the postcondition you obtain in the conclusion is the end of the postconditions on the individual hyperterms, T1 and T2. Okay, so this is our goal from before. And we are in this awkward position of trying to align the assignments twice with the one in the component 1. And if we are pedantically using the alignment strategy here, we are already stuck because the 2 programs do not have the same structure. They are not both sequential compositions, right? And so previous logic could deal with this because they pushed the expressivity by allowing some slack here and there. here we don't need that ad hoc solution. We just can reason with our core principles. And so the first thing we do is to say, okay, we first want to break up component 2 into 2 separate assignments, right? And so to focus on a single component, we can apply nest in one direction and realize that this can be split into disjoint terms. And we apply it and apply nest, and we put the first component on the outside and the second component on the inside. What have we accomplished here? We accomplished that we can focus on one of the weakest pre and manipulate it, while having frozen the other term without having to express what it does in an assertion. We kept what it does implicit in the term there. It's sitting there. We are receiving the postcondition whatever it did to the hyperstore, and then we continue asserting over it, right? And so what we can do is then apply the sequence rule just to the inner weakest pre and break it up into 2 pieces, the 2 assignments. At this point, we can apply the nesting again and unfreeze only the 2 assignments we care about. We put them together in the union of these 2 hyperterms, and we obtain that we align them. Progress. Now, the problem is the postcondition is not the one we can discharge with just determinism, right? It has this weakest pre in nested position. But we can realize that, well, we have the assumption that op does not modify x nor y for that matter. And so the postcondition on x1 and x2 is independent from it, and we can apply the frame rule. We can prove it outside of the weakest pre that is the nested position. And then we have a conjunction in the postcondition, and so we can decouple the 2 proofs. We can prove the 2 conjuncts independently. And this is the case of the conjunction rule where the 2 hyperterms were the same hyperterm. So perfect overlap. And the first conjunct happens to be our determinism hypertriple. And now we are left with the other. And here what we want to do is to take the assignment in the first component and align it with the one inside. How can we do that? We apply the nest again to break that hyperterm up, and then we apply it again to merge it with the inner one. And now we realize that the postcondition alone here is our axiom on commutativity. And the axiom on commutativity said no matter what the state is, this holds. And so it will hold also in the state resulting from running the first assignment. And so we can discharge that condition, and we are done with the proof. The only real new ingredients we needed were with these very 2 simple composition principles. And the crucial idea is that you keep computation implicit, and with the ability of manipulating this weakest pre more flexibly, you are able to keep it implicit for as long as possible. These are not the only principles that are needed to really carry out the proofs we want. There are these other 2 classes that I'm not going to go into. And, well, to reiterate, that's the key insight of LHC, that you can keep proof relational and compositional if you keep computation implicit. There's future extensions that are possible, and we are excited about them. There's possibility of adding separation or concurrency to the language, to the logic. Probabilistic extensions are also rather relevant, and we want also to push this to more expressive quantifier alternation. And of course, implementation would be nice. Thank you.
Here, probabilistic. Very good. Yeah, so we have all coffee break for questions.
Thank you for the interesting talk. So you said that your hyperstores are finite partial maps. Is there a reason for that? Do you need it for soundness?
The hyperterms.
Yes, and the hyperstores, I think, also.
No, we were just looking at case safety, and I haven't looked at the infinite case because I didn't have any use case for it.
Okay. You could have, for example, proving that the mean response time of something is smaller than something, and here you need to have all the executions. And another question is, you have this slide where you say you remove program alignment and you say this is the other one, but isn't it both? Because you use a lot of, in a sense, program alignment to do your proof, right? And if you want to automate, you need to reason about maybe not program alignment, but some alignment.
Absolutely. We don't reject program alignment as a principle. That's good. And when it works, that's what you should do, right? It's not the only thing that matters. And we are basically saying, okay, we can actually explain program alignment using slightly more fundamental, simple compositions. That's still a surface level proof principle you want to use. So we're not rejecting program alignment at all. This is what you want to do, but you need to be a bit more flexible if you want to apply it compositionally.
Yeah, great work. So I have a question about your overlapping union. Like, do you need some condition over the, operations? Like, how do you tell whether two operations are duplicates, whether they might have side effects, right? So, I mean, those are not a general function call, right? They are primitive operations or what?
No, so there is no real constraint on the code of the hyperterms. What matters is the indexes. So you have to keep in mind that terms at different indexes will be applied to completely different hyperstore, like completely independent. So even if they assign to the same variable, they would not interfere with each other. And the union here is on the indexes. Right? So we are not going to confuse the hyperstores.
You do have overlapping unions, like something appear twice, and then you need to tell whether they are, alpha equivalent or truly same thing. Or...
no, so the union requires on the overlap that you map on to the same term.
Okay.
Syntactically the same term.
All right. Okay.
Yeah.
Yeah, there's more behind you.
You didn't show your rule for loops, and typically in two hyper safety logic, you have restrictions on the invariant, like the invariant needs to be unary, or you need to prove that the loops are going to have exactly the same number of iterations. Can you comment on, do those LHC help with that? Do you have lighter restrictions?
Excellent question. So our rule is actually the unary one, and the beauty of it all is that through manipulation of weakest pre, you don't need more, even to express the usual lockstep same number of iterations. So the lockstep number of iteration rule in LHC is a derived rule that you can obtain from manipulations of the unary while rule and the other weakest pre proof rules. And the way you use it is actually very interesting, and is one of the things that I think are more impressive of the logic. It allows you to express loop invariants with weakest pre in it. And that's what allows you more slack in the alignment, because you can talk about the other execution in the other loops more flexibly, because you can embed it in the loop invariant now. But there's no time to go over this example, but offline I can give you.
So thanks for the talk. In the future work slide, you wrote mechanization. So currently, is this implemented in Coq, Isabelle?
Paper.
Okay.
It's a great system. I recommend it.
Sure. So do you have an intuition of how complex the proof search here is? Does this flexibility essentially allow for factorial growth with the reordering or something like this?
Yeah, so the proof rules are like one advantage of the previous approaches is that the proof rules tended to be more syntax directed. Although, if you needed, the moment you needed more flexibility in the alignments and the alignment was not perfect, you would need, I mean, the syntax will not direct the search anymore, and you would still get an unbounded search space there. So the way they solved it there is to throw at it clever heuristics so that you can guide this search. And I don't see any obstacle in doing this here, but now we need heuristics that talk about compositions of weakest spree. And so I see it as an opportunity to do some new, to develop new heuristics for the search.
I have a question about your, I think it was nesting, the multiplication thing. It reminded me kind of a separation logic star. Is it something similar, or could you think of it? Because you're kind of separating, not here, it was earlier, I think, but you're separating on the terms, no? You're
Yeah,
splitting the terms into two disjoint parts where you cannot overlap.
Yeah, we had a version that worked with separation, actually.
Okay.
But we found that the issues we were looking at were orthogonal to the what separation brought to the picture, because the separation you get among components is very trivial. It's just by construction. They will always be working on different stores. So it was not bringing much to the picture. But the separation logic extension hopefully would bring out some nice interaction with the separation on the single component. That's something we are looking into. Cool.
Yeah, coffee, I guess. There's no more questions. Then let's distinguish Emanuele with the final round.